So, I was busy last time with the air intakes or inlets with the external flow. And we explained that there are two forces that we need to add to the problem. One of them is what we have called the additive drag. The additive drag. And this is a drag, so this is, let's say, a negative thrust. And another one is the lip suction thrust. This is, let's say, a thrust, so this is a positive thrust. And of course, we need to take the balance of these two. So one has a positive sign and the other one a negative sign. So you need to write that, for example, like this. And the difference between the two is what we have called the spillage drag, or spill. And this is a drag, so this is a negative thrust, okay? And we have explained that this one is independent of the inlet geometry. It's only depending on two parameters, for example, the Mach number and also the mass flow ratio, that we have also called AA divided by AI. Whereas the lip suction thrust is a function of the geometry, of the Mach number, and of the mass flow ratio. So, and of course, if you make the balance, this is also a function of the geometry, the mass flow ratio, and the Mach number. Okay? And why is it important to mention that? This is in the frame of the understanding and the build-up and the computation and the definition and also the announcement of the performance of the aircraft. Because the manufacturers, they need to build up an aerodynamic database, database, and they need also to build up a propulsion database. And they will compare these two in order to extract the performance of the aircraft. And this is something that they make beforehand, before the first test, or certainly manufacturing and test flight of the aircraft, only based on the market, only based on what they know of this one, and they build up an hypothetic aircraft that will answer to the needs of the market. And this is a big problem, as I explained to you last week, because in this problem, they are testing an aircraft in a wind tunnel, but the aircraft in the wind tunnel that is tested here, we need to test it, of course, for different flight Mach number. We need to test it for different, let's say with a certain speed, angle of attack. And this angle of attack is related with the aircraft gross weight. Let's say its structure, its payload, the amount of fuel you have on board. But it needs also to have, due to these features, you need to have there the engines. And the engines must be with a certain mass flow rate going through the engine. And that means that in these very expensive aerodynamic wind tunnels, you are introducing a new parameter, which is the mass flow rate. You would need to make the test for different flight Mach numbers with different angle of attack and with a third parameter multiplying, let's say, by 1.5, by increasing by 50% the number of tests that you need to do. And this m dot is, of course, related to the AA divided by AI that we have defined before. And this is something that they cannot allow. And so they will do the test with this for only, at each Mach number, one only m dot. And for the other m dot at this Mach number, they will do something else. So what will they do, in fact? They will define for each MA, they will define a certain m dot corresponding with this MA, and with this m dot is corresponding a certain AI, AA divided by AI. This is what we have called the capture area ratio, the capture area ratio I. And so what will they do? They will define for each Mach number a certain m dot, a certain capture area ratio, and they will do the testing. And so in the CL, so they go to the wind tunnel, and in the CL and in the CD that they are obtaining, in fact, this CD is containing the CD additive and the lip suction thrust. So it's containing, in fact, the CD spillage. It's containing the CD spillage for what they call the capture area ratio baseline. So in these tests that they are doing, are measuring on the aerodynamic balance, it's including this and this. So it's including this, as this is the sum of the other two, but only for the baseline, the reference that they are taking corresponding for each Mach number with m dot and AA divided by AI. So it's not enough. What they have must be, let's say, added. They must correct, let's say, the parameters that they have with something else. They need to take into account the difference that is existing between the CD spillage, let's say, real, if you want, minus the CD spillage for the capture area ratio baseline. When I say real, there is a real capture area ratio. And so they need, in fact, to understand what is, for each Mach number, the influence of the other values of AA divided by AI compared with the capture area ratio baseline that you have defined. So you see, they are computing, you need to have a delta CD spillage that is considering the value that is already included in your force computations with the real one. And how can they do that? How can they do that? They will build, in fact, a small intake, a much smaller model of the intake, going to the entrance of the compressor, that is the section A1. Of course, you have here, in cruise or not in cruise, the fictive divergent from the section AA until the section between this point and this point that we have called AI. And they will test this at different Mach numbers, with different m dot. So for each Mach number, they will test that with different m dot. Of course, also with the capture area ratio baseline, or the m dot baseline, but also with all others. And what will they do? They will make holes here in the external face of the intake. If this is a symmetric or non-symmetric intake, it is not very important. And they are measuring here the pressure. And they integrate from this point to this point. They will integrate between the section AI and the section A1, the Pi, let's say P, because I is also this one, the P that they have in different places, minus P atmospheric, multiplied by ds, and so like this, they will obtain the LST, the lip suction thrust, for the different Mach and the different m dot. Of course, it's not enough, because you need also to have the influence of the additive drag that is here. But this part is not difficult to have, because we know that the additive drag is only equal to the CD additive that we have explained last week, that is, let's say, always the same value. It's just a function of the Mach number and AA divided by AI. So this is a given table or a given equation or a given figure multiplied by 1/2 rho A VA square multiplied by the surface, which is the section AA. So it's quite easy because when you know the mass flow rate, you know AA, you have VA that is related with MA, 1/2 rho A multiplied by this factor that is coming from this figure. And you do that also for different Mach numbers and different m dot. And so you have this coming from computations, and you measure this. And this measurement is, of course, much easier, much less costly than working in a wind tunnel. It's just a small wind tunnel that you can build there on the table. It's very easy to make. It can be a scale model of the intake and very easy to do and very low cost measurements. And like this, you will define the CD spillage real, if you want, or it depends how you are counting that, the variation compared to the CD spillage baseline that you had measured in the wind tunnel. And using the wind tunnel, measuring that, and using the small intake tunnel, measuring this and computing that, you can obtain the CD spillage outside of the baseline, non-baseline if you want, and you have everything that you need. Okay? And that can give you a complete aerodynamic database. Also, I need to explain why they are proceeding like that. In fact, the problem is not as easy as what I'm explaining here. Because the problem is valid for the engine considering the small divergence that you have here at the entrance. This is section AA, this section AI. Here somewhere you have the section A1, and here somewhere you have the section A5. In fact, we have always considered that the exhaust nozzle was delivering an ejection speed like this one. But the problem is there identical to what we have in the intake. So you see the intake, it has a shape that is like this, and here the exhaust, it has a shape that will make that the exhaust will be in this way. So you will have an exhaust flow that is going in this direction, and in fact, what you would need to, let's say, consider in the computation would be to consider the section here where the flow is really cylindrical. Where the flow is really cylindrical. And this is a section that is smaller than A5. And this is a speed here that will be higher than this one. This one is higher than this one, a smaller section but a higher speed.